Welcome back to Math TV with Professor V. This is a continuation for Chapter 9 lecture on hypothesis testing. So we're going to start looking at the z-test for a mean and actually crank out some hypothesis tests, first by hand, and then I'll jump into StatCrunch. So the z-test for a mean is a statistical test for the mean of a population. And it can be used when the population is normally distributed and sigma, which is the population standard deviation, is known. Note, these are the same conditions introduced for when we use z-confidence intervals that we learned about in Chapter 8. And many test value formulas for statistical tests follow this basic format. The test value is equal to the observed value from your sample minus the expected value divided by the standard deviation or standard error. So the test value formula for the z-test is as follows. Z equals x bar. That's what we observe. That's our sample mean, right? That's why that's the observed value. Minus mu. Mu is expected. We never actually have or can find mu. We just assume or expect it to be equal to something. Divided by the standard deviation. And you probably remember sigma over rad n. That's standard error of the mean back from the central limit theorem a few chapters ago. Okay, you can memorize this if you want, put it on your note card. We're going to use the formula when we do the hypothesis test by hand to get the test value. But like you know, for your exams, you're going to be using StatCrunch, so you don't have to put this to memory unless you want. And then I went back and I pulled the critical values, or the z sub alpha over 2's. They're going to be the same thing. This is back from Chapter 8, okay? Remember we talked about alpha already, and I listed out for you guys some of the common values. So when alpha is equal to 0.10, then that means you split 0.10 on each of the two tails. That's how a confidence interval worked. So you had 5% on each side, and then z sub alpha over 2 was 1.65. At 95%, z sub alpha over 2 is 1.96, and 99% z sub alpha over 2 is 2.58. So this comes from confidence intervals, which are always two-tailed, always, right? But we can still use these values for our hypothesis test, even if they're one-tailed, just pick the right one. I'll show you what I mean in just a second. Don't fret. Okay, let's get into an example. It has been reported that the average credit card debt for college seniors is $3,262. Oh my goodness, that is a lot. The Student Senate at a large university feels that their seniors have much less debt than this. So it conducts a study of 50 randomly selected seniors and finds that the average debt is $2,995. with a population, standard deviation of $1,100. Using alpha equals 0.05, is the Student Senate correct? Okay, so state the hypotheses and identify the claim. There's a lot of numbers going on in the problem. Don't let it freak you out. Notice here in the second part, I actually don't want you to look at the first part of the problem right now. It says this Student Senate conducts a study of 50 seniors. Okay, so that's your sample. N is 50. And it finds that the average debt is $2,995. That's the sample mean. That's your X bar. With the population standard deviation of 1,100. So sigma is 1,100. What does that mean? This 3262, that's not from a sample. That's just what's reported. So that's what it's believed the population mean is equal to. Okay. So the hypothesis null is always going to be mu equals what? 3262. Identify the claim. What's the alternative? Well, if you read that second sentence, it's in there. It says the Student Senate feels their seniors have a debt much less than this. So they're claiming, the Student Senate is claiming mu is less than 3262. That's the claim. Okay. Good. Determine the significance level. Well, it's been given to us. Alpha is 0.05. But is this test left-tailed, right-tailed, or two-tailed? Well, to decide, remember, you look at the alternative hypothesis. Since mu is less than something, then this is a left-tailed test. Okay, I'm going to draw you an arrow to help you know. I knew that from the alternative. So what does that mean? That means alpha, that 0.05, that area needs to be in the left tail of my normal distribution. So over here, this is all 0.05. Okay, this would be my rejection region, critical region, right here. This is the non-critical or non-rejection region. Let me switch up the wording. Okay. Find the critical value or values. Well, since this is a left-tailed test, we only have one. The critical value is the value that separates the rejection region from the non-rejection region. And you can think back to those z sub alpha over 2 values that I gave you in chapter 8. The critical value, notice it separates 0.05 area on the left. When we looked at z sub alpha over 2 for confidence intervals, it was two-tailed. So if you had another 0.05 on the right, yeah, then that would correspond with 0.10 being alpha. This is already it cut in half, yes? So 1.65 is going to be the critical value, but I'm going to make it negative because it's to the left of the mean. Okay, good. And again, when you do these in StatCrunch, it's going to give you all of this so you don't have to memorize anything, really. Now let's compute the test value. Okay, so to get the test value, we're doing a z-test for the mean. So I'll write out the formula again. Z equals x bar minus mu over sigma over root n. So x bar, you can scroll up, we listed it all out, right? 2,995 minus mu, 3,262 over sigma, 1,100 over root n, rad 50. And this you can just put in your calculator. I usually round to like 2 decimal places. So take a second, do that, and you should get negative 1.72. That's the test value. So look back. Here's our graph. That critical value, remember we said it was at negative 1.65. Where does the test value fall? In which region? Negative 1.72 would be somewhere over here, right? That's where my test value is. The test value is in the critical region or the rejection region. So now it's time to make our decision. Are we going to reject or not reject the null hypothesis? Well, it's in the rejection region, so we're going to reject the null. And then now let's summarize the results in terms of the claim using a complete sentence. So first you either say there is or there is not. If you reject H naught, then you say there is. If you fail to reject H naught, then you say there is not. Okay? So in this case, there is sufficient evidence to, and then I'm going to say support the claim. Why? Because the claim was in the alternative. To support the claim that seniors have, what did they claim? An average debt less than $3,262. So basically what we said was the mean from the sample, 2,995, was different enough from 3,262. It was so different that it was in the critical region. It wasn't just by chance. It must be that our original hypothesis is wrong. The mean really isn't so extreme. It's not 3,262. Okay? Good. Let's do a couple more. Oh, yes. Okay, example 2. A real estate agent claims the average price of a home sold in Beaver County, Pennsylvania is $60,000. A random sample of 36 homes sold in the county is selected, and the sample mean is $82,496 with a population standard deviation of 76,025. At alpha equals 0.05, is there enough evidence to reject the agent's claim? All right, so state the hypotheses and identify the claim. It's pretty clear. They say it in the first sentence. The real estate agent claims that the average price is $60,000. So H naught is going to be that mu equals 60,000. That's the claim. And the alternative is just that it's not 60,000. We're not interested in one direction or another. Then let's see what other info was given. A random sample of 36 homes, so N is 36, is selected, and here's the sample mean. So what's that? That's your X bar. X bar is 82,496. And we have a population standard deviation, that's sigma, 76,025. Okay, good. Determine the significance level. Well, they told me alpha equals 0.05. At this step, I also want you to say, is it left-tailed, right-tailed, or two-tailed? We'll look at the alternative. Since we have a statement that involves not equal to, not an inequality, then this is a two-tailed test. So what does that mean? That means we split alpha between the two tails of the graph. So 0.05 gets cut in half. So you have 0.025 here and then 0.025 here. Okay. Good. Find the critical value or values. In this case, we're going to have two because it's a two-tailed test. So plus or minus, and it's always the same number. If you remember from your confidence intervals, this is at 1.96 and this is at negative 1.96. So you could just put plus or minus 1.96. Good? Okay, let's keep going now. Let's compute the test value. So same formula. Test value, this is a z-test. It equals x bar minus mu over sigma over rad n. So x bar, that's the sample mean. We listed it up there. 82,496 minus mu is 60,000 divided by sigma, that's 70, that's a very large standard deviation, over rad n, rad 36, which is 6. Okay, punch that all in your calculator. And I ended up with 1.78, as should you. So let's see, in which region is 1.78 gonna fall? 1.78 is somewhere around here, yeah? And remember, this is the non-critical region or non-rejection region. So that means our decision is that we fail to reject the null. We're not in the critical region. Our test value is not more extreme than the critical value. So we're going to fail to reject the null. We don't accept the null. Do you see that? We just failed to reject it. We can't say it's false. So summarize the results in terms of the claim using a complete sentence. So this time I'm going to say there is not, since we failed to reject, sufficient evidence to, instead of support, this time I'm going to say reject the agent's claim. Why? Because the claim was in the null hypothesis this time. The agent's claim that the average price of a home sold is $60,000. I mean, if you can get a car for that now, that's good. I don't know where you get a house for $60,000. Okay, so just to make it clear when you're summarizing, these are the things that will change. Is not, is, reject, or support. And here's how you figure it out. If you, in step 5, reject H naught, then you say is. If you fail to reject H naught, you say is not. Okay? If the claim is in the null, then you use the word reject in part 2. And if the claim is in the alternative, then you use the word support. You won't have to really write out summaries by hand too much because, again, we're going to be using StatCrunch. But back in the day when I first taught stats and I was handing out tables, everyone had like 5 different tables on their desk. It was a mess and they had to write everything out. They had to know all this. Okay, I have one more by hand for you, okay? And then we'll get into StatCrunch. The average production of peanuts in Virginia is 3,000 pounds per acre. A new plant food has been developed and is tested on 60 individual plots of land. The mean yield with the new plant food, is 3,120 pounds of peanuts per acre, with a population standard deviation of 578 pounds. At alpha equals 0.05, can you conclude that the average production has increased? Okay. So notice here, this 3,000 pounds, that's my mu. Okay, and then here's n equals 60. The mean yield from that sample of 60, that's my x bar, that's 3,120. And here's my population standard deviation, so that's sigma. And they want to know if we can conclude or claim that the average production has increased. So let's see, null, that's easy. It's always mu equals, in this case, 3,000. Production increasing would mean that mu is more than that number. Mu is greater than 3,000. So that's the claim. Okay, the claim is in the alternative. All right, let's determine the significance level. They gave it to me. They said alpha is 0.05. So let's decide, is the test left, right, or two-tailed? It's right-tailed, yes? Very good, because the alternative has greater than 3,000. Okay, so if we were to look at our distribution, we would need all of that alpha, that 0.05, to be in the right tail here of the graph. Okay. Find the critical value or values. There's only one because it's right-tailed. If there's 0.05 in one tail and you want to think back to your z sub alpha over 2's, then it was 0.1 divided up between the two tails. So this is at 1.65. So critical value is 1.65. And then now let's compute our test value. So z equals x bar minus mu over sigma over rad n. X bar, where do you go, x bar? X bar is here, 3,120 minus mu is 3,000 over 578 over rad 60. Okay, punch that in your calculator. Round to 2 decimal places. What do you guys get? 1.61. Okay, so where does that fall? Is that more extreme than our critical value? It's so close to it, but no, here's 1.61. So this is the non-critical or non-rejection region. 1.61 is not more extreme than our critical value. So what's our decision? We do not reject the null. We fail to reject H naught. And then let's summarize, okay? So there, do we say is or is not? Is not, because we failed to reject the null. There is not sufficient evidence to, do I say reject or support next? Check, where was the claim? In the null or in the alternative? It was in the alternative, so that means you use the word support when you're summarizing. If the claim was in the null, you would use the word reject. Okay, so there's not sufficient evidence to support the claim. What was the claim? That average production has increased above 3,000 pounds per acre. All right, very good. So this is the traditional method for hypothesis testing. We have another method that in actuality is used a lot more often in actual statistical studies. If you read research journals, the p-value method is the one that is actually used more often. So hypothesis testing, the p-value method is just a different method for conducting a hypothesis test. Whether you do traditional method or p-value method, the result is going to be the same. It's just a different way of going about it. The decision will be the same. The conclusion will be the same. Many scientific studies present the results of a hypothesis test in terms of the p-value. If a hypothesis is tested at the same significance level using the traditional and p-value methods, then the conclusion would be the same for both approaches, as I said earlier. So terms to know. The p-value is the probability of getting a sample statistic at least as extreme as that observed if the null hypothesis were true. So if the sample statistic would be highly unlikely or not probable if the null hypothesis were true, our conclusion would be that the null hypothesis is not true. So basically, like if the sample statistic is almost impossible to happen, assuming the null is true, then you go, oh, well, I got a sample with that mean or whatever. So that means my initial assumption of whatever the null is must be wrong. Think of the p-value as a way to measure the strength of evidence. A small p-value means stronger evidence. So to find a p-value, again, we always interpret the probability as the area under the appropriate distribution curve to the extreme side of the test value. So in this case, if we're going to do a z-test, it's under the z-curve. If it's left-tailed, it's to the left of the test value. If it's right-tailed, to the right, or two-tailed, it's going to be the area in each of the tails together. And here's the basic decision rule for all hypothesis tests done using the p-value method. If the p-value is less than or equal to alpha, remember small p-value, strong evidence, then you reject the null. If the p-value is greater than alpha, then you fail to reject the null. All right? And when a hypothesis test is performed using the p-value method, the significance level alpha is chosen by the researcher before the test is conducted. However, some researchers choose to report the p-value and not the alpha value, leaving the decision whether to reject H0 up to the reader at their desired alpha level. And you might start noticing this now. I don't know if you read any research studies, but they'll tell you what the p-value is. And then you can see, oh, would we reject the null or fail to reject the null depending on what different alphas are, right? Because, you set the alpha. If that's going to change the decision, maybe you want to set it differently, depending on the context of whatever the research is, okay? So let's get into an example. To do these tests using the p-value method, we have to use StatCrunch. So let me show you how. All right, so let's do some hypothesis testing in StatCrunch. And you'll notice they actually do the traditional and p-value method, both of them, for a lot of the exercises. First one, a sample mean, sample size, and population standard deviation are provided below. Use the one mean z-test to perform the required hypothesis test at the 5% significance level. So they give us x bar, that's the sample mean, n, that's the sample size, sigma, that's the population standard deviation. That's important that they gave that to us. And then null hypothesis mu equals 35, alternative mu is less than 35. So first thing, bam, right off the bat, they want the test statistic. You could do it by hand, but let's use StatCrunch. So open it up and then notice you're going to go stat, z stats, one sample. And we don't have data, we have summary. They gave us the mean, standard deviation, etc. So sample mean, just enter all the info here. X bar, that was 33. Standard deviation, 7. Sample size, 36. And perform a hypothesis test for mu. So leave it selected here. Mu is equal to, this needs to be 35. And then the alternative, drop down and select less than 35. Okay. And then just click compute. So there's our z test statistic. And they want us to round to 2 decimal places. So that will be negative 1.71. If we're rounding to 2 places. Fantastic. Moving on. The p-value, well, it's right there. They give it to us as well. Rounding to 3 decimal places, 0.043. All right, easy enough. And now we have to make a decision about the null hypothesis. So remember, if the p-value is less than or equal to alpha, you reject the null. What was alpha? Alpha is the significance level here. So 0.05, since 5%. Is 0.043 smaller than alpha? It is. So that means we will reject the null hypothesis. The data provide sufficient evidence to conclude that the mean is less than 35. That was what our alternative hypothesis stated. And let's check. We filled in everything well. So these are much easier than the 6 steps when you do them by hand, but I wanted to show you the old school way, you know, so you appreciate how good you have it. Okay, next problem's more or less the same. Shouldn't be too hard, so I wanted to do another one. Let's redo it. I'll start reading it to you. Cadmium, a heavy metal, is toxic to animals. Mushrooms, however, are able to absorb and accumulate cadmium at high concentrations. A government set a safety limit for cadmium in dry vegetables at 0.5 parts per million. The cadmium levels in a random sample of one species of edible mushroom are in the accompanying data set. Okay, so they're going to give us a bunch of values. At the 5%, my brain already makes it 0.05. Okay, significance level. Do the data provide sufficient evidence to conclude that the mean cadmium level in this species of mushroom is, pay attention, greater than the government's recommended limit of 0.5 parts per million? Assume that the population standard deviation of cadmium levels in this species of mushrooms is 0.32 parts per million. That's super important that we include that, okay? The population standard deviation. Preliminary data analyses indicate applying the z-test is reasonable. So basically, you don't have to stress, pick z-test and, you know, carry on with your life worry-free. So first, we're just going to state the hypotheses, okay? Null always will include equality. And the limit is 0.5 parts per million. 0.5. Alternative, that's when I raised my voice and read it all slowly. It's right here. Is there sufficient evidence to conclude that the mean cadmium level is greater than the government's recommended limit? So right there, alternative is going to be greater than. Always keep the number the same, okay? You're not going to switch it from the null to the alternative. Doesn't happen. Check it. I don't need to. We're always right. Okay. Compute the value of the test statistic. So this is when we're going to use StatCrunch. So open the data in StatCrunch. Yes. And then you do have to be careful. Since they gave us the population standard deviation, I need to include that. Okay. So same thing, stat, z-stats. It's only one sample. Don't worry, you'll get to pick that 2 samples sooner enough with data. And we're using all of the data in column 1, standard deviation. It says optional because you don't always have it, but they gave it to us. The population, second to last sentence, a population standard deviation is 0.32. If you forget to put it in, you'll get the wrong answer. Okay? And then make sure you choose the correct or enter the correct hypotheses, null and alternative. So I'm going to change this to 0.5. And then alternative is that mu is greater than 0.5. And that's it. So let's compute. Here's my z-test statistic, 1.21, right? If we're rounding to 2 decimal places. Well done. And they want the p-value, 3 decimal places on that one. So that'll round to 0.113. Ooh, 3. Nice. And anything else? Okay. So alpha was set at 5%, significance level 0.05. Look at the p-value, 0.113. That's larger than alpha. When p-value is larger than alpha, we fail to reject or do not reject the null. Remember, small p-value means strong evidence. At the 5% significance level, the data does or do not provide sufficient evidence to conclude that the mean cadmium level is more than. I was looking for greater than. They didn't have it. More than means the same thing. So that's the one we're going with. Fantastic. Okay, last one I'm going to do from this section has to do with connecting Chapter 8, confidence intervals, with hypothesis testing in Chapter 9, and to help you kind of see the connection between the two, okay? I don't want you to have them as like totally separate concepts in your head. So here it gives you a little blurb kind of to motivate what this problem's all about. Read it carefully. For a two-tailed, it must be two-tailed, hypothesis test at the significance level alpha, the null hypothesis H naught of mu equals mu naught. This just means, some proposed population mean, that mu naught, will be rejected in favor of the alternative hypothesis HA, which is mu is not equal to mu naught. That's what makes it two-tailed, that it's just not equal to. If and only if mu naught lies outside the 1 minus alpha level confidence interval for mu. Illustrate the preceding relationship by obtaining the appropriate 1 mean z interval for the situations described in parts A and B below. So it might sound confusing, but hopefully when we work through these next two little parts of this problem, it'll connect the two concepts, okay? Don't get scared. So A says, the average lactation period of all earless seals is 23 days. For a sample of 14 female gray seals, the average lactation period is 22.3 days. It is assumed that the population standard deviation is 3.0 days at the 5% significance level. The data do not provide sufficient evidence to conclude that the mean lactation period of gray seals differs from 23 days. So they've already done a hypothesis test at the 5% significance level, and they said, we're going to fail to reject the null. The data does not provide sufficient evidence to conclude the alternative. So now they're asking us, okay, we did a hypothesis test for you. Find the confidence interval. Okay, no problem. We're professional at that. So we're going to go z-stats. Again, one sample, this time with summary, right? So sample mean, 22.3. Standard deviation, population standard deviation was 3 days, and the sample size was 14 female gray seals. We're not doing a hypothesis test. This time they want us to do a confidence interval. The confidence level is 1 minus alpha, 1 minus 0.05, so 0.95 is correct. Alpha right here, 5% significance level, is 0.05. So let's go ahead and compute this confidence interval and round to 2 decimal places. So lower limit, 20.73, and then upper limit, 23.87. Look at the population mean. The population mean is 23 days. That lies within this interval, okay? So what does that mean? Well, since the population mean is in the confidence interval, right? 23 lies between the lower limit and the upper limit. This does not provide sufficient evidence to conclude that the average lactation period of gray seals differs from 23 days. This is the same conclusion reached by the hypothesis test. Remember, in the hypothesis test, they said the data do not provide sufficient evidence to reject the null. And that's because the sample mean is not different enough from the proposed population mean. So that's the same thing as saying, hey, it lies within the confidence interval, so I'm not going to reject the null. It looks like it's checking out. Yeah. And then let's just do one more. So according to researchers, the mean length of imprisonment for motor vehicle theft offenders in a nation is 16.9 months. What nation? I don't know. 100 randomly selected motor vehicle theft offenders in a city in the nation had a mean length of imprisonment of 17.7 months. It is assumed that the population standard deviation, blah, 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 is 5 months. At the 5% significance level, the data do not provide sufficient evidence to conclude that the mean length of imprisonment in the city differs from the national mean. So they already told us we're going to fail to reject the null. So take a guess right now. Will mu lie within the confidence interval? Yes or no? Okay. So let's try. Let's see. Let's get that confidence interval. So Z stats, one sample with summary. What was the sample mean? Not the first number. That's the population mean. 17.7. Standard deviation 5. Sample size 100. They wrote it in words. That can be tricky. And then this time we're doing confidence interval. 5% significance level means at the 0.95 confidence level. So it looks like we're ready to compute. Again, rounding to 2 decimal places. So lower limit 16.72 and upper limit 18.68 if we round. Excellent. And then last part, look at the population mean. It was 16.9 months, yeah? Does that lie within this interval? It sure does. So since the population mean is in the confidence interval, this does not provide, it's not different enough, right? Does not provide sufficient evidence to conclude that the mean length of imprisonment for motor vehicle theft offenders in the city differs from the national mean. This, you're always going to put this, is the same conclusion reached by the hypothesis test. It shouldn't be different unless you do it wrong, okay? So that's it. You guys should be good to go. Let's jump back into the lecture notes, and then I do have another example to show you. All right, you guys are doing great. One last idea, the t-test for a mean. So that's another statistical test for the mean of a population. And it can be used when the population is normally or approximately normally distributed. And then here's the clincher, sigma is unknown. So we don't have the population standard deviation. Instead, we have S, the sample standard deviation. And this should sound familiar. These are the same conditions introduced for t-confidence intervals in chapter 8. So see your notes on t-confidence intervals for a review of the t-distribution. Remember, it has degrees of freedom. It's a family of curves. And here's the test value formula for the t-test. Almost identical to z. Look, t equals x bar minus mu over, only difference here is that we have s instead of sigma over root n. Degrees of freedom equals n minus 1. So let's just hop into StatCrunch right now, and then I'll show you how to conduct a t-test for a mean in there. Okay, t-test time. Not much is going to be different. You're just going to select t. Question we're going to work on here. Suppose a study reported that the average person watched 4.59 hours of television per day. A random sample of 15 people gave the number of hours of television watched per day shown. At the 10% significance level, do the data provide sufficient evidence to conclude that the amount of television watched per day last year by the average person differed from the value reported in the study? And notice here they actually give us X bar and S. So they give us the sample mean and standard deviation, and they gave us the data. So really it's up to you. You can put the data in StatCrunch, but we really don't need to. They gave us the summary, so it's up to you. You could do this problem either way. First, we're just going to set up the hypotheses for a one mean z test. So the proposed population mean is right here. Suppose a study reported that the average person watched 4.59 hours of TV per day. So mu, always with an equal sign, 4.59. And then for the alternative, look here, this last statement. Do the data provide sufficient evidence to conclude that the amount of television watched per day differed? So just not equal to. It didn't say greater than, less than, whatever. Always the same number. Okay. How much TV do you watch a day? I mean, trying to think. the test statistic is. So here we go, stat, t-stats. I'm not putting that data in StatCrunch. You could, whatever you want to do. One sample, and I'm just going to say with summary. So sample mean, they gave it to me there, 4.293. Sample standard deviation is S. That's going to be 1.135. And the sample size, in the second sentence, it said a random sample of 15 people. And then just change the numbers for the hypotheses. So mu equals 4.59. I love that here in StatCrunch it changes, so the null and alternative have the same number. And that's pretty much it. So compute. Let's see here. It doesn't make it bigger. I don't like that. Okay. Where is my t-test statistic? Right there. Negative 1.01. Negative 1.01. Okay. The p-value, round to 3 decimal places. That's all they gave me anyhow. So 0.328. And let's compare the p-value with alpha. So alpha is at the 10% significance level. That's 0.1. But the p-value is 0.328, way bigger. So remember, if p-value is larger than alpha, then we do not reject the null, fail to reject. That means the data do not provide sufficient evidence to conclude that the amount of television watched by the average person is different from the value reported in the study. So remember, small p-value, strong evidence. Large p-value, high probability, very likely. So we're not going to reject anything. Okay, this one is nostalgic. I'm doing it in honor of my father because I remember being a young child and there was a National Geographic television special about this topic. And he had me sit down and watch it with him, and I was traumatized, needless to say. So, alligators perform a spinning maneuver referred to as a death roll to subdue their prey. In a study of alligator death rolls, one of the variables measured was the degree of the angle between the body and head of the alligator while performing a roll. A sample of 20 rolls yielded the data provided below in degrees. At the 10% significance level, do the data provide sufficient evidence to conclude that, on average, the angle between the body and head of an alligator during a death roll is greater than 42 degrees? Again, they gave me X bar and S, so I could open the data here if I want, but we can look at it. Then you'd open it in StatCrunch. We don't need to. And then they're telling us here, you can reasonably use a t-test. Great, thank you. So they'll always let you know. Okay, null hypothesis is that mu equals, what's the proposed value? 42 degrees. And alternative, I saw the word greater, so that's what we're going to select here, greater than 42 degrees. Don't put the degree sign, just the number. Okay, now we need the t-test statistic, so stat, t-stats. It's just one sample. I'm going to do with summary, kind of easier. Sample mean, 42.27. Sample standard deviation, 12.426. Sample size, it was 20 rolls, right? Yes. And we have mu equals 42, and then change the alternative. Don't forget, greater than 42. Good deal. And here we go. So the test statistic is here, 0.097, only 2 decimal places though. So 0.097 is going to round to 0.10, correct? Correct. And then the p-value, 0.4618, that's going to round to 0.462. Excellent. Again, really big p-value, 0.462. We have a 10% significance level, that's 0.1, and p-value is larger than alpha. So again, fail to reject the null. Do not reject the null. The data do not provide sufficient evidence to conclude that the average angle between the alligator's body and its head is greater than the hypothesized mean. Okay, and the rest of the homework you should be fine to do. There is another example, the last one, that links again confidence intervals and hypothesis testing, just like I showed you with Z confidence intervals and hypothesis tests. So it's the same thing. Just choose a T interval. And that's pretty much it. If you have never seen a video of an alligator death roll, I highly encourage you look it up on YouTube. It's fascinating. You can't really escape it. So just make sure you don't get caught in one, okay? Happy studying. I'll be back to do chapter 10 shortly. Give the video a thumbs up if you found it helpful. Subscribe if you haven't already. And I'll see you guys soon.